Now we're going to be learning about the case where we have bivariate data. So now we have bivariate data. So whereas before we had univariate data, we were looking at one variable. Now we're going to be looking at two variables. And these variables, usually we have one that's independent, called x. This is the one that we're going to change. We're going to alter its value. Then we have another dependent variable called y, and we're going to see how y reacts to a change in x. So then we're going to graph the points xy on a plot called a scatter plot. So we're simply going to label all the points where x is on our x-axis, it's our independent variable, y is on our y-axis. So we'll graph all the points, and our goal is to find a relationship or trend between x and y. And once we find this trend, we want to be able to describe its strength, the strength of this relationship. So is it a very strong relationship? Is it really clear that x and y are related? Or is it a weak relationship? And the way we do this is by expressing the relationship in terms of a function or a linear function. We'll express y in terms of an intercept. So a, that's our intercept, and some slope b times x. And what we get is essentially a line of best fit that describes the best general trajectory or relationship between x and y. And the way we find this line of best fit, so we find the line of best fit in a manner where we minimize the distance or the average distance between all points and the line. So if this was the distance between this point and the line, this was the distance between that point and the line, the way we calculate the line is in a way such that the line we find has the minimum average distance between all the points and the line itself. And so this is very similar to minimizing the variance from the points to the lines in a sense. And so just like our variance had a term where we had the point minus the mean squared, the method that we use to find the line of best fit is called the least squares method, since we're minimizing all these square terms. So recall that the general equation for a line of best fit is equal to y is equal to a plus bx, and sometimes is written as y hat for a line of best fit. And the way we calculate this line is in a way that we minimize essentially the variances. And so we're going to introduce three variances. One variance is going to be for x specifically. So this is equal to x, and it's not exactly a variance. So our variance, if you remember, was s squared is equal to the sum of all the square differences from the points and the mean divided by n minus 1. So it turns out that we don't care about this n minus 1 part. We only care about the sum of all the differences, and this is what we call a variability. So now we're going to calculate three different variabilities. And we're going to use the shortcut method. So this was equal to the sum of all the points squared. So we square all the points and add them, minus however many points there are times the mean of the points squared. So we're going to use that shortcut first for all the x points. So the variability for x is equal to the sum of all the x points minus the mean of x, which is equal to the sum of all the x points, we square them, then we add them up, minus however many points we have for x times the mean of x squared. So we only consider the variable x. We do the same for y, so s y y, that's going to equal the sum of all the y points, the differences between the y points and the mean of y, which is equal to squaring all the y points and adding them up, minus however many points in y there are, so it's going to be the same amount for n between x and y, multiplied by the mean of y squared. And then we're going to do it for the product between x and y. So we're going to have pairs x and y. In the first case, we look at x only. The second case, we look at y only. We then multiply them, find their pairs, and look at that. So s, x, y. And this is called the covariance when you divide it by n minus 1. But we're looking at the covariability. This is equal to the sum of the differences between x and y. So x minus its mean times y minus its mean. And that's equal to finding the products and adding them up minus however many points you have for x and y, so n, times the mean of x times the mean of y. Once you have these three values, you can calculate b in this equation for the line of best fit. B is going to equal s xy, so the covariability, divided by sxx, so the variability in x, and essentially this is giving us how the two variables change with a change in x, which is why it gives us the slope. And then a is equal to the mean of y minus whatever you found for b times the mean in x. So you find those two, you plug them into your equation for your line of best fit, and you will find it. So here's a data set where we have x, we have y, and we have 5 points in between. So we've done an experiment 5 times, we've changed x and found how y changes. And now we want to find the regression line, or the line of best fit, for a scatter plot if we drew it. Now we've eased the calculation for this problem by giving the sum of all the x points, the sum of all the y points, the sum of all the x points when they are squared, the sum of all the y points when they are squared, and then doing the same for the products. We don't really care when they're squared, so we did not include that part. I do encourage you to try to do this problem without this extra aid, but since the video will be too long without it, we opted in. So we'll begin to find the line of best fit. We'll begin by finding the means for x and y. So the mean for x is equal to sum of all the x points divided by however many there are. So the sum of all the x points is 15 divided by, there are 5 points, so the mean of x is 3. The mean for y is equal to the sum of of all the y points divided by however many there are, so 5 once again. That's equal to 412.6 divided by 5, which is equal to 82.52. So that's the mean for y. Now, sxx, which is the variability for x, is equal to squaring all the x terms, so 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, and adding them, minus the number of points times their mean squared. So the sum of all the x points squared is 55, minus 5 points, and their mean is 3 squared, and that comes out to 10. So the variability in x is equal to 10. SYY, or the variability in y, and you'll notice that we don't actually need this for the regression line, but we're going to need it to calculate the strength of the regression line, which is coming in a couple of minutes, so we're still going to calculate it. It's equal to the sum of all the y points squared minus number of y points times their mean squared. So that's equal to the sum of all the y points squared is 335,111.1 minus 5 points, and the mean is 82.52 squared, and that gives us an answer of 106.348. And Sxy is equal to the sum of the products between x and y, so 62.5 plus 147 plus 243.6 and so on, minus the number of points, so 5, times the mean, or we'll write the equation first, the number of points times the mean of x times the mean of y. So the sum of all the products is 1340.1 minus 5 points, the mean of x is 3, the mean of y is 82.52, and that comes out for a variability of xy of 102.3. So now our equation for the line of best fit is in the form a plus bx, where b is equal to sxy divided by sxx, so 102.3 divided by 10, which is equal to 10.23. So our slope is 10.23, and if you had units, you could feel free to include them. And then for a, that's equal to the mean of y minus whatever we got for b, so 10.23, times the mean of x. So that's equal to 82.52 minus 10.23 times our mean of x is 3. And that's equal to 51.83. So we plug this in to our equation for the line of best fit, and we get a final answer for our line of best fit is equal to 51.83 plus 10.23x. And if you graph this line along with the points in a table on a software such as Desmos, you'll see that in fact it is the line of best fit. And if you use any software like Google or Excel and you calculated the line of best fit for these points, you should get something very similar. Now, there are multiple cases for some trends. For example, I could have a very clear trend where all the points line up very clearly in a line. I could also have a trend where I can essentially force a line of best fit, but it's not as clear. And then I could have the case where all my points are just randomly placed and there is no clear line to place. And so we want to be able to express how strong or how clear is our relationship. And sometimes the relationship between x and y is called a correlation. And the way we do that is by using two coefficients called regression coefficients, the first of which is r, or the correlation coefficient, and r is the ratio between the covariability sxy divided by the square root of sxx times syy. So that's why we calculated syy, because eventually we do need it. And sxy can be negative or positive depending on whether our correlation is going up, so as x increases, y increases, or whether it's going down, so as x increases, y decreases. So r can also be positive or negative, but it's bounded between 0 and 1. So the absolute value of r is greater than or equal to 0, less than or equal to 1. R can be negative or positive, so it can go from negative 1 to positive 1. If r is equal to 1, it's a very strong positive correlation. So that's what you're seeing in this first picture over here. If r is equal to 0, there is no correlation. So that's what's happening down here. If r is between 0 and 1, then there's a moderate correlation. If it's greater than 0.8, it can be considered strong. And if it's below, it's moderate. And if it's below around 0.5, it's pretty weak. So that's what you're seeing in this case. And if r is equal to -1, then it's a strong negative correlation. So essentially, the closer the absolute value of r is to 1, the stronger the correlation. Now if we square r, we get r squared. That's called the coefficient of determination. So r squared is equal to sxy squared divided by, we get rid of the square root, sxx times syy. That's r squared. And since we're squaring it, this value of r squared is between 0 and 1. It cannot be negative. It still stands that the closer this is to 1, the stronger our correlation. But in this case, r squared is more so telling us how good the model or the line is at predicting the value of y based on x. And more specifically, whatever the decimal value you get for r, it represents the percentage of the change in y that can be explained by x. So if I get a r squared value of 1, that means 100% of the change in y can be explained by change in x. If I get an r squared value of 0.7, then only 70% of the change in y can be explained by the change of x, and the other 30% can be random or due to other factors. And so the closer the value is to 1, the stronger the relationship between x and y is. Now finally, it's not really wise to strictly depend on these values to identify a correlation, since as you can see, I could have a correlation where my points do have some relationship in the form of a parabola, but if I use the model we just introduced, which is a simple linear regression model, so every time my model is going to create a linear line, it's not going to create a parabola, so it won't recognize this as a relationship. I might still get a flat line and I'll get a low r value, but that doesn't mean that there isn't a relationship between x and y. So you should always use these as tools to help you, but you should always look at the graph to make any final decisions. Finally, if you do find a strong correlation, a correlation does not imply causation. So just because x and y are very strongly correlated, it doesn't mean that a change in x causes a change in y. It just might mean that they're connected in some external way. So now we're asked to find the strength of the regression or the line of best fit or the correlation that we found earlier in an earlier question. So I'll remind you that the variability in x that we had in the earlier question was equal to 10. The variability in y was equal to 1063.348, and the variability in xy was equal to 102.3. So now to find the strength, we're going to calculate both the correlation coefficient and the coefficient of determination. Starting with the correlation coefficient, r is equal to x, or sxy, divided by the square root of sxx times syy. That's equal to 102.3 divided by the square root of 10 times 1063.348, and that's equal to 0.99205. And that's essentially telling us how well our line of best fit fits the data points. So since this is very close to 1, we have a very strong correlation. And our model is very good at describing the points. Now, if we calculate r squared, or the coefficient of determination, we can simply square the value that we found above. So 0.99205 squared, and that's equal to 0.984 approximately. That's also very close to 1, and it represents that, therefore, around 98.4% of the change in y can be explained by change in x. So the correlation, or our model, between x and y is very strong. Since only about 1.6% of the variation y is random or due to external factors. So our final conclusion is that the correlation between x and y in the previous question is very strong.